Hello, welcome to another module in this Maths Open online course. So, let us continue our discussion on the application of matrices and linear algebra, and in this module let us start looking at another very important and interesting area of application, and that is related to circuits. Alright, so circuits and circuit analysis is one very important area where these principles of linear algebra can be applied. Let us consider a simple circuit that is shown below. These are the different resistances, and you have another resistance here. Let us start putting the values. This is 4 ohm. So, hopefully all of you have seen this kind of circuit before. These are the resistances. This is a 1 ohm, this is a 2 ohm, this is again a 4 ohm, and this is an 8 volt, and this is a 4 volt battery, right. And so, we want to analyze this circuit to determine the currents in the different branches, right. So, determine in this circuit we want to determine right. So, once again linear algebra can be used for the analysis of circuits, that is what we were saying. So, what we were saying is the fact that this linear algebra and principles of linear algebra can be used in the analysis of circuits. All right. So, we want to determine the currents in these branches. So, we use a technique that is known as mesh analysis. So, what is this mesh analysis? In each mesh we have a separate current. So, this is the current in mesh 1, this is the current in mesh 2. So, naturally this current will be I 1, this current will be I 1, this current will be I 2, this current will be I 2, this will be I 2, and this branch which is both in mesh 1 and 2, you can see there is a current from mesh 2 to the right, current from mesh 1 to the left. So, this will be I 2 minus I 1 to the right. So, these are this is the mesh analysis. I 1 and I 2, these are the mesh currents, right. So, we are going to use the principles of mesh analysis to determine the currents. What we have is we have these two independent meshes. So, we have the current I 1 in mesh 1, I 2 in mesh 2, and the edges that overlap or the elements that overlap between these meshes, you have to determine the currents appropriately, like what we have determined in this circuit. Okay. Now, the other principles that we are going to use is we are going to use KVL. I think most of the people in electrical engineering, I mean even basic engineering, because this is taught as a core course. So, most of the students who are in engineering and also for that matter science should be able to appreciate this KVL, this is Kirchhoff's voltage law, which basically states that the net voltage drop across a loop is 0. the net voltage drop across a loop is 0, and plus we are going to use another law, that is the Ohm's law, which of course most of you should be again familiar with, which is the voltage drop across resistor. This is a linear element, that is the voltage drop across resistor. That is, let us take a look at this resistance plus or minus, and then you have this resistance R, you have the resistance R, and then you have the current, you have the current I, right. So, you have V equals IR. So, voltage drop, so the way to read this is the voltage drop in the direction of the current. The voltage drop across this resistance in the direction of the current, that is, we are going in the direction of the current across a resistance of value R, the voltage drop across that resistance is given as V equals IR, okay, in the direction of the current I. Alright. So, now let us go back to our circuit and let us start the analysis of our circuit. Let us start traveling clockwise in this. If you travel clockwise, let me just write these equations here so that you will be able to follow this. If you go to clockwise, if you call this loop 1 and if you call this loop 2, clockwise going in loop 1, you start with the battery element. So, there is an 8 volt drop plus resistance 1 ohm, I 1 ohm times the current I 1 in the direction of the current, and then you have minus, because now in the 4 ohm we are going opposite direction of the current. So, drop will be minus 4 times I 2 minus I 1 equals 0. So, this is basically your loop 1, and if you look at loop 2, once again starting with the 4 ohm resistance, now you go in the direction of the current clockwise, 4 times I 2 minus I 1 plus the 2 ohm resistance 2 times I 2 plus now the 4 volt battery 4 plus now the 4 ohm resistance 4 I 2, this is equal to 0. So, this is basically both of these. So, this is for loop 1, this is for loop 2, both are these are obtained using KVL. So, both of these follow from essentially KVL, which states that the Kirchhoff's voltage law, which states that the net voltage drop across a loop is basically 0. Okay. So, now let us simplify these equations. Let me rewrite these equations for both the loops. So, loop 1 we have, well, 8 plus I 1 minus 4 I 2 minus I 1 equals 0. This implies 5 I 1 minus 4 I 2 equals minus 8, and for loop 2 we have 4 I 2 minus I 1 plus 2 I 2 plus 4 plus 4 I 2 equal to 0. This implies that well, minus, I am sorry, 4 times I 2 minus I 1, 4 times I 2 minus I 1 plus 2 I 2 plus 4 I 2 equals 0. This implies 10 times minus 4 I 1 plus 10 times I 2 equals minus 4. So, put these equations together now, 5 I 1 minus 4 I 2 equals minus 8, and then you have minus 4 I 1 plus 10 I 2 equals minus 4. You put these things as a matrix, you will have the matrix 5 the system of linear equations. So, 5 minus 4 minus 4 10 I1 I2, this is equal to minus 8 minus 4, this implies I1 I2. So, this is of the form now A and the current vector I bar is equal to B bar. So, I1 I2 equals A inverse B bar, and now you know how to compute the inverse of a 2D matrix. So, this is 1 over the determinant 1 over 50 minus 16. So, 1 over 34 times swap the diagonal elements, negative of the off diagonal elements, that is the inverse of the 2 cross 2 times minus 8 minus 4, and if I simplify this, therefore, if I simplify this, what you will have is you will have the currents I1 and I2 that are basically determined as minus 48 by 17 and minus 26 by 17. So, the mesh current I1 equals minus 48 by 17 and the mesh current I2 equals minus 26. So, these are the mesh currents. Alright, so basically what you have seen is linear algebra can be used to solve circuits, and especially it is very helpful to solve very large circuits. And in fact, this is one kind of analysis. You can also do an equivalent analysis to find the node voltages. In fact, that will then use Kirchhoff's current law, which states that the current that is entering any node, net current that is entering any node, or net current that is leaving any node is basically 0. Alright. So, that is known as the KCL, right, that is the Kirchhoff's current law. This is the KVL, what we have used as the Kirchhoff's voltage law to find the mesh currents. So, therefore, what this shows is matrices playing a very important role. So, the idea here is to show through this simple example a very important role matrices play a very important role in solving large circuits, right. So, that is the point. So, linear algebra and matrices in general have a number of applications in the analysis and solution of circuits. Alright. Let us look at another interesting example, that is to solve traffic flows, analyze traffic patterns, for instance in cities across roads, and this can be used for public transport and so on and so forth. So, traffic flow problems, again another interesting application of this is to basically analyze traffic flows. How do you apply this to solve? Once again, let us take a simple example. Let us take an example of a grid of roads. So, you have a city which is in blocks, and then you have the grid of roads. So, let us look at the traffic. So, for instance, you have a flow of 75 vehicles, you have a flow here of 50, you have a flow here of 45, you have a flow here of 55, and now you have these unknown flows. So, this is the flow of 80. Now, let us denote the unknown flows. For instance, this is the first flow x1, x2, x3, and this is the unknown flow x4, and these are the intersections A, B, C, D, these are the intersections. Now, we need to find the traffic flows. So, we need to find the traffic flows find the unknown traffic flows x1, x2, x3, x4, and once again we can use the same principle similar to Kirchhoff's current law, same principle, that is the traffic entering any intersection has to be equal to the traffic leaving that intersection, otherwise there is going to be a progressive build up of traffic in that intersection, which is unsustainable, right. So, that is the principle. So, this can be solved using the principle. So, what is the principle? Simple principle to analyze the traffic flow. What is the principle? For each intersection, for each intersection incoming traffic has to be equal to outgoing. Therefore, the following equations must hold. Therefore, the following equations must hold. Let us just write it over here, probably because you will find it simple, because we have this figure over here. So, if you look at intersection A, we must have 75 plus x4 incoming traffic, 75 plus x4 must be equal to 50 plus x1, that is 75 plus x4, I am sorry, this has to be 50 in this direction. 75 plus x4, that is the incoming traffic, must be equal to 50 plus x1. This implies that x1 minus x4 equals 25. For this intersection, we must have the incoming traffic x1 plus 45 is equal to x2 plus 80, that is the outgoing traffic, which implies that x1 minus x2 equal to 35. For this intersection, we must have x2 plus x3, that is the incoming traffic, is equal to 35, x2 plus x3 equal to 35. And this intersection of course is simple. This intersection is simply x4 plus 55, that is outgoing traffic, x4 plus 55 equals the incoming traffic, which is 35, which implies x4 equals minus 20. All right. So, using this principle at each of the 4 intersections, we have been able to find the system of equations. Now, all we have to do is we have to write the system of equations in the form of a matrix, and then you can use the solution of the system of linear equations to solve this traffic flow problem. All right. So, essentially what we are going to now write this as, write the 4 equations. You have x1 minus x4 equal to 25, x1 minus x2 equal to 35, x2 plus x3 equal to 35, and x4 equal to minus 20. So, now you are going to write this in the form of a system of equations. You write you write the matrix. What is the matrix? That is 1 0 0 minus 1 1 minus 1 0 0 0 1 1 0 0 0 0 1 and therefore, you can write this as this times x1, x2, x3, x4, this is equal to your 25, 35, 35 minus 20. What does this imply? This implies, of course, now you have another system which is of the form Ax bar equal to b bar. So, you have Ax bar equal to b bar. This implies that x bar equals A inverse b bar, and if you solve this system of equations, you will find that the solution is basically 5 minus 30, 65 minus 20, all right, and therefore, we can determine the traffic flows as x1 equal to 5, x2 equal to minus 30, x3 equal to 65, x4 equal to minus 20. So, these are basically your traffic flow. So, you can check and verify these things, all right. So, that is interesting. So, essentially what you have seen in this module is basically seen how powerful linear algebra can be with diverse applications. We have already seen it's employed in wireless technology. We also now seen that can be employed in traffic flow analysis, can be employed in circuit analysis, and we will see more such applications, and we will continue to see more such applications as we go through this course, all right. So, let us stop here and let us continue in the subsequent module. Thank you very much.